Next problem is to find the Fourier series coefficient value. So that's the Fourier series analysis of this waveform, in particular the a sub naught through a sub 2, b sub 1, and b sub 2. So there's three ways to do this. Let's start off with the good way. The good way is to evaluate the integrals. So that's a naught is equal to 1 over t times the integral over any time period, your v of t dt. So you'd have to choose one time period. I'd probably choose this one right here. Similarly, your a sub n is equal to 2 over t times the integral over any time period of v of t times your cosine of n omega naught t dt, and you could figure out your b sub n's the same way, except it'd be multiplied by sine. There's a better way. Just by inspection, you can see that the average value of this thing is 1. So therefore, your a sub naught is equal to 1. That's one integral less. The second is to realize that this equation, this function, is even. You can flip it around that vertical axis and you get the same number. So therefore, all of your b sub n's are 0. And now you just need to evaluate your a sub n's using that equation. And you've cut down your work by over half. But the best way of doing it is to recognize that the opposite of the Fourier series analysis method is the Fourier series synthesis method. And that says that you can recreate your original waveform by these sums. And so on. But when you compare that to what's given, you can instantly see that your a sub naught term is 1 from here. Your a sub 1 term from here is 1. Your omega naught, which isn't even asked for, but it's easy to read off from that, is 2. Your theta 1 is 0. There's nothing over here. And there's no higher order term. So a sub 2, etc., and v sub 2 and higher, they're all equal to 0. There's nothing out here. There's nothing more to this equation that's given up here. So therefore, your a sub 0 term is equal to your capital A sub 0 term, which is 1. And you can create your a sub 1 minus j b sub 1 term as a complex number, like this. But since your capital A sub 1 is 1, and it's at an angle of 0 degrees, that means that this, your a sub 1 term, has to be just equal to 1 minus j 0. So that's another way of seeing that you're, from here, comparing these values, that your a sub 1 term is equal to 1. And let's see, it asks for your b sub 1 term. You can see from here, b sub 1 is 0. And since all your higher order a sub 2, v sub 2 terms are 0, when you take a look at it in this complex domain, to convert it from capital A phi into little a b, you can see that all these other terms are also going to be 0. And so there it is with almost no work. Second, if the waveform was very slightly shifted to the right, which components would increase, decrease, or stay the same? So there's a good way of doing this, And that's to say that if we want to shift it to the right, I'll call our new function v naught v prime. That doesn't mean the derivative of v, that just means it's our new function that's been shifted to the right. That's the same as our original function, just with t replaced by t naught, if we want to shift it to the right by t naught. So given what we were given at the start, our new function would look like this: cosine of 2t minus t naught. So that shifts it to the right by just a little bit. Since it's a small amount, let's make it something specific. Let's say it's 0.1. So now it looks like cosine of 2t minus 0.2 for a 0.1 shift to the right. So using the best way up here, we can see that our a naught is, for this, is still this value here. It's unchanged. And because of that, our a naught, little a naught, is always the same as our big A naught, and that's unchanged. Our a sub 1 at an angle of phi sub 1, we're going to have to work out the math for that. That's going to be equal to 1 at an angle of, from over here, minus 0.2. And that is, in rectangular form, 0.98 minus j 0.2. So this is our a sub 1, and this, not including the minus sign, is our b sub 1. So our a sub 1 was 1 up here. It goes down to 0.98, so our a sub 1 decreases. Our b sub 1 was 0, and now it's increasing up to 0.2. And you could do the same analysis for your a sub 2 and b sub 2 components. Now there is a very clever way to simplify this still further. And that's to say that as we shift it to the right, this 1 plus cosine of 2t, as we shift it to the right more and more, there'll be a constant subtracted from the 2t. And this constant will eventually, at some point, approach pi over 2. And that's a critical value, because whenever you subtract pi over 2 from a cosine, that's the same thing as saying it's sine. So I want to make clear that this is a equals. As we delay it more and more, what we begin with, 1 plus cosine of 2t, starts to morph into 1 plus sine of 2t. And now you can directly compare that versus the Fourier synthesis version. And the Fourier synthesis, remember, says that your original voltage waveform is equal to your a naught component plus some amount of a1 times cosine of omega naught t plus your b1 times your sine of omega naught t plus, and you can continue that out, a sub 2 cosine of 2 omega naught t, and so on and so on. Now compare it to what you've got here. As your delay approaches this value, your a sub naught term stays 1. It stays unchanged. But your a sub 1 term, now, there's no cosine. So this goes to 0, so this decreases. As the delay approaches a value that would give you this number, your a sub 1 decreases. Your b sub 1, though, goes up to this coefficient, this implied 1. So this increases. And your a sub 2 terms and your b sub 2 terms, there never was them before. They're still not there. So your a sub 2 and b sub 2 terms stay unchanged. So that's your answer. A sub naught unchanged, a sub 1 decreases, b sub 1 increases, a sub 2 and b sub 2 are both unchanged.